Now, in this video, we're going to be talking a little bit about the remainder and factor theorems. They're closely related ideas, and sometimes it's useful to be able to swap them back and forth when you're dealing with trying to find the zeros of a polynomial that does not necessarily factor very easily. Now, the idea behind the remainder theorem basically says that the remainder from dividing by x minus c, the factor x minus c, is equal to f of c. And the factor theorem, again, in its sort of summary form, says that if f of c is equal to 0, then a polynomial divides evenly by x minus c, which is to say that if p of x is your polynomial, then x minus c is a factor, and when you divide it out, you will get a quotient that is just a polynomial with no remainder. So that's why these are related to each other. If the remainder is 0, then x minus c is a factor. And that is also equivalent to saying that if I evaluate the function and I get a 0, then then I also have this as the remainder. So the remainder and factor theorems are closely related to each other, and sometimes that makes it easier for us to test functions, particularly when you get a lot of experience and practice doing synthetic division in particular. You get really good at evaluating a function that way, and that's, in fact, sort of how it was. One of the reasons why synthetic division is so useful is because it does allow you to have a different way of evaluating a long polynomial that involves only addition and multiplication and no exponents. Whereas if you're evaluating the polynomial directly, you have all these exponents, and sometimes when you can get very large numbers. Synthetic division gets you the same answer, because if you have a remainder, that's the value of your function. And the fact that these remainders and the function values are related, again, makes this connection a very useful one. So we want to go through and do an example so that we can see how this actually works. So we can do it with both synthetic division or with long division, because it's just about what the remainder is, not the process that you use to get there. So let's look at a specific example. Let's say I have x squared plus 8x, that's not an 8, plus 15, and I want to see if c is, what is f of negative 5? Now, what we can do is we're gonna evaluate it in the function, and then we're gonna do the division, and we're gonna see that they're the same value. So first, let's do it the sort of old-fashioned traditional way. F of negative 5, we'll actually just plug it in and see what happens. So we've got negative 5 squared plus 8 times negative 5 plus 15. Negative 5 squared is 25. 8 times negative 5 is negative 40 plus 15. This is equal to 0. So what this is telling me is that this is a 0 of the function, according to the factor theorem. Then I should be able to do the division, get 0 remainder, and write my function as, in this case, x plus 5, because x minus a minus 5 would be x plus 5, and some polynomial that divides out evenly. So let's try this. I'm going to draw it out by hand because the notation for doing this manually is quite a pain. So let's give ourselves a little space. So we have our division bar, and we've got and I'm going to do long division. Again, synthetic division works exactly the same way. I mean, the process obviously is different, but the meaning of the result will be the same. Now, x minus 5 is equivalent to dividing by x plus 5. Now, how does the division process work? And we go over this example in another video, so you can certainly watch that other video. We take our leading term into our leading term, x squared divided by x. That gets me an x. I multiply x squared plus 5x. Then I'm going to subtract. And 8 minus 5 is 3x plus 15. And then I divide again. X goes into 3x 3 times. I multiply. 3 times x is 3x. And 3 times 5 is 15. I subtract, and I get a remainder of 0. So again, remember, what does this mean? This means that f of x, which was x squared plus 8x plus 15, can be written as a factor, x plus 5, and something else. And we find out that the something else in this case is x plus 3. And you can see, if you go back and you think about like, how would I factor this? Factors of 15, which add to 8, would be 3 and 5. I mean, this makes perfect sense in this case where we have 0 as our value at this particular number. And again, this is going to work regardless of how long the polynomial is. If you, again, assuming you don't make any arithmetic mistakes, you can use synthetic or long division to do the division. It's always the factor is x minus c. So if you're evaluating f of c, flip the sign, do your long division, or keep the sign and do your synthetic division. But think about it in terms of what you're doing with your factor, and assuming that you, again, don't make any arithmetic mistakes. This can be also a nice way to sort of check your algebra. Because you know what the remainder is supposed to be if you plug the value into your function. So if you're doing your long division and you find out like, I didn't get that remainder, then you know that you've made a mistake along the way. And it's a useful sort of cross check when you're doing all of these steps, and you can lose minus signs and things like that along the way.